Hi everyone, welcome to the Z module on rotation and angular momentum. So the Z module is going to present about the introduction about the angular momentum and few related examples. And then we extend the theory to the multi-particle system. We end up with the application of angular momentum. So to start with a simple example, we consider an object which is moving in a circle with the help of the rope. So man is circling a particle in radius r which has got a mass m, and with the help of the rope the man is able to rotate the mass in a circular pathway. So this mass is moving with the velocity v. So what will be its linear momentum? Obviously we know the linear momentum is nothing but m into v. But it's quite surprised to say that this particle, apart from this linear momentum, it also possesses angular momentum. So what is that angular momentum? So if the mass moves in a rotational motion, then obviously it acquires rotational motion in additional to the linear momentum. So what is that angular momentum? Angular momentum is nothing but mv cross r. What is mv? Linear momentum. What is r? R is nothing but the radius or the distance at which the particle is rotating about a circular path. So the rotation leads to angular momentum. And what is this conservation of angular momentum? According to the conservation of angular momentum, the total angular momentum of any isolated system remains constant. So for example, before rotation, if the ball possesses the initial angular momentum as mvi ri, what is vi? It's a velocity at the initial position, and ri is radius at the initial position. So after going through a complete circular rotational motion, if the final angular momentum is mvf rf, if both the initial and final, if it gets add together, if it is equal to 0, then it states that the angular momentum is conserved. So the conservation of angular momentum goes in this way. The initial angular momentum is equal to the final angular momentum. Since in both the cases there is no any change in the mass, so in short we can say that it's a product of VI RI is equal to the product of VF and RF. F stands for final position, I stands for the initial position. So how it gets equal? If for example, if any case, if the radius gets smaller, obviously the velocity becomes larger to make the product the same. So let's see a few examples, then it will be clear, more clear. So here you could see, if even if we shorten the string, that is, if we shorten the rope at which the ball is rotating, then obviously if the radius is decreased, then the velocity will be increasing. So if the radius increases, the velocity will be reduced. So you could see the difference in the first two pictures. In the first picture, you could see an appreciable distance or length of radius r. But whereas in the second picture, the radius is reduced to its half. So obviously what happens to the velocity? The magnitude of the velocity will be much larger. So the smaller radius, higher velocity, making the product remains the same, which is nothing but the conservation of angular momentum. The same example here, you could see a man who is just moving around with the dumbbells. So what happens if the ball speed increases? If the ball speed increases, obviously the string length will be shortened. So the boy spins faster when he pulls in his arms. When he pulls in his arms, obviously the product remains equal. The final position, at the final position, the product of velocity and radius remains equal, making the angular momentum conserved. So here again an interesting example where you could find a scatter who's spinning faster. See, you see the two cases. When the scatter pulls her arms and legs inside, she is able to spin faster because she is reducing the radius, making the velocity larger, which means that the angular momentum remains constant or conserved. So here again a related example, you could see the earth is at the center and the point A and the point B represents the position of the satellite. As the satellite moves from A to the point B, what happens? It moves faster than at A because obviously the radius between the Earth and the point B is decreased, but to compensate this decrease in radius, the velocity will be greater, which makes the angular momentum conserved. So here there is again a simple example for you to have a better understanding about this angular momentum. You just imagine a ball which is attached to the end of a 1 meter string. That is, the length of this rope is 1 meter, and which is where this mass is moving at the speed of 10 meter per second. So this is what its initial condition. Now the question is, find the ball speed as you shorten the string to 2 centimeters. So if you reduce this r 2 centimeters to 10 centimeters, or we can say that around zero point 0.1 meters, then what happened to its velocity? Obviously you can make use of this conservation law of conservation of angular momentum, where the product of the initial velocity and the initial distance should be equal to the product of the final velocity and the final distance, which will yield the final velocity, which is nothing but 1 into 10 divided by zero point 0.1, which is nothing but 100 meter per second. So the velocity, if the velocity will be larger, if the radius is reduced, then the velocity will be larger. So hope you could got the point. So the conservation of angular momentum is nothing but V cross R is equal to, that is V1 cross R1 is equal to V2 cross R2. The initial uh, product of velocity and the distance is equal to the final product of final velocity and the distance. So here again, to have a better clarification, so what is momentum? Momentum is nothing but it contains by the virtue of its motion, which is always proportional to the object's velocity. So the velocity, the linear momentum, is more concerned about the object's velocity. But whereas the angular momentum is proportional to the object's angular velocity. That is, if the object moves in the rotational motion, then the angular momentum merely depends upon the angular velocity, where the angular momentum L is nothing but the product of I omega. What is I? I is nothing but the moment of inertia. So all these definitions holds good only for the rigid bodies, because it varies from bodies to body. It varies with respect to the bodies, and here the angular momentum and angular velocity is parallel to one another only if the object is symmetric around the axis of rotation. And so here this is the example where to understand better. So here again, what is this angular momentum principle? So the angular momentum principle is nothing but what is change in angular momentum with respect to time, that is dl with respect to dt. What is dl by dt? We know what is l. What is l? L is nothing but r cross p. So we can just separate accordingly. So by keeping p as a constant and differentiating with respect to t first with RA, and then by keeping RA constant and differentiate P with respect to T. So obviously you'll be getting two different terms. The first term, when you look into the first term, what is RA by dt is nothing but V. And what is MV? Again, V cross V. V cross V becomes 0. So the first product vanishes. And what happened to the second term? The second term we left out with the RA cross dP by dt, which is nothing but, what is dP by dt? F. That is, F is equal to m into a, or F is equal to the rate of change of momentum with respect to time. So R cross dP by dt is nothing but F. So R cross F is nothing but tau. So the equation goes in this way. That is, dLA by dt is equal to R cross F, which is equal to tau. Or I can say that the change in angular momentum with respect to time is nothing but your torque. So the angular momentum principle is nothing but it's derived from the principle of momentum. The same how the momentum varies with respect to time, the same way the angular momentum also varies with respect to time. So here again a good example for you to correlate. So here you could see a kind of a spanner which is used to tighten the screws. So here there are three pictures. The first picture where the direction represents the force, right? And this is force. The arrow mark represents force. And obviously you know the distance. What is this RA? RA is nothing but the distance from the force at which it is applied to the point at which the screw is getting tightened. So this horizontal distance is your RA, and this arrow mark is nothing but the point at which the force is applied. So now the question is, you could see three cases here. So which case corresponds to the largest torque? And you know the torque is nothing but the product of the radius into the net force. So obviously in this case, so r cross f, or cross is nothing but rf sine theta, right? So in this case, the direction of r is in the horizontal direction and the f is in the vertical direction, making an angle 90 degree, which means that sine 90 becomes 1, which is the maximum value. So tau will be maximum in the case A. What happens to the case B? So here the direction between R and F seems to be 0, which means that sine 0 is 0, which makes tau as minimum. So the case B has got a minimum torque, whereas case A has got maximum torque. And what happens to case C? See, there is some similarity between A and C. In both the cases, the direction of the force is in the upward direction. But what happens to the distance? Here in the case A, R has got a maximum distance, whereas in case of C, R is comparatively less than the case A. So obviously the product of R cross F is less in C than in A. So when you compare the three cases, the case A corresponds to a largest torque. I hope the question is clear for you. Right. Now, what happens to the direction of the torque in case B? In case B, what happens? Since there is same direction, theta is 0, so tau is 0. So obviously the option C is the right answer. It has no direction since it is 0. Right? Right. So the next example is about the conservation of angular momentum. So you could see the change in angular momentum in the system plus the change in angular momentum in the surroundings, both together, if it is added together, it will be equal to 0. So here there is a simple example. You could find an athlete who is moving around an elliptical pathway. So here in this case, when this athlete moves around this elliptical pathway, again the angular momentum at its surroundings will be equal and opposite. When it is added together, it remains conserved. Similarly, inside the system, if we find the angular momentum, it also remains conserved. So on together, if we add the angular momentum of the system as well as the angular momentum of the surroundings, put it when it's add together, it becomes 0. And again, the comet, here there is a simple example for you to understand about the motion of the comet. So here what happens to the comet if it is placed at the point B? So at the point B, due to the gravitational pull, the direction of the torque will be at this point B. So we can take this, if we divide this into quadrants, the point B lies in the negative y direction and R is in the positive x direction. So obviously the Z will be in the, so that is the torque will be in the Z direction, which means that it will be out of the page. It will be out of the page, right? And the next relative example is about the Kepler's laws. So we all know that a radius vector which is joining any planet to the sun. So this that is the point which is on the outer circle is nothing but the planet and the sun is at the center. So the radius vector which joins any planet to the sun sweeps out equal areas and the equal lengths of time. And again, this is also because due to the conservation of angular momentum. And again, there is another example for you to understand. For example, you just imagine a ball which is falls straight down in the xy plane. So its momentum is shown by the orange color arrow mark. And what is the direction of the ball's angular momentum? So obviously when the momentum is in the xy direction, the angular momentum will be in the z direction. So here it is positive x, positive y. So obviously the positive z is the direction of angular momentum, as the angular momentum is nothing but the cross product of r cross p. So the cross product of a positive x and positive y will always result in the positive z direction. So again, there is a simple example. You can imagine a planet which is orbiting a star in a circular orbit in xy plane. So its momentum is shown by the red color arrow mark. What will be its angular momentum of the planet with respect to the star? Again, the same case. If the planet orbits the star in the xy plane, then obviously the angular momentum will be in the z direction, which means that in the out of page, that is in the positive z direction. So if we extend this conservation of angular momentum to a system where it consists of multi-particles. For example, you could find mass M1, M2, M3. So obviously this mass M1 has got one external force F1, and this M1 will do have got an impact over the second mass as well as the third mass. Similarly, if I do have got the mass M2, and if this mass M2 is acted upon by an external force called F2, then this force, or which is attributed by the mass, will do have got an impact over the mass M as well as the mass M3. Similarly for the third mass. So how can we write the change in angular momentum with respect to the time for the first particle, that is for the mass M1? So in case of mass M1, and this F1 is the external force. So the first factor will be due to the external force. So R1 cross F1. And the second factor will be this R1 will do have got an impact over the second mass, which results in the force called F12. So the second factor will be R1 cross F12. And the third part is again the same mass will do have got an impact over the third mass called M3, which has got a distance of around R1 cross F13. So similarly, we can write it for the change in angular momentum for the second mass as well as for the third mass. So here you could see some sort of similar terms which is appearing. So here there is F12 and F21. So both are equal and opposite together, which cancels each other when we add all the three terms. And again, F13 is equal and opposite to F31. F23 is equal and opposite to F32. So all the three terms will get cancel each other, and you will be left out with only the contribution of the external forces in each case. So the angular momentum of the first mass, angular momentum of the second mass, angular momentum of the third mass will be nothing but the product of R1 cross the first external force, R2 cross second external force, and R3 cross the third external force. So likewise, we can extend it to the multi-particle system where the conservation of angular momentum holds in the same way. And here there is a good comparison between the momentum and the angular momentum, which also can be correlated with the energy. So the net force which is acting on the system is nothing but the rate of change of momentum. So if the momentum changes, then it might be due to the net force which is acting on the system. So what happens to the angular momentum? So if the angular momentum changes, which results in the torque in the system. So there is no any external force, so the momentum remains constant. And here, if there is no any external torque, then the angular momentum remains constant. And more specifically, the location of the object is not at all a matter in case of momentum, but whereas the location of the object relative to the particle or the referred point is thus matters a lot. So this is what the unique difference between the momentum and the angular momentum. Location does not matters in case of momentum, whereas location matters a lot in case of angular momentum. And we'll look about this energy extension later in this next module. So again, the angular momentum, which is nothing but a system with no torque. So here there is an example for you to have a better understanding. The similar example, the skater who is having an initial moment of inertia greater than the final. How come? As we told that the angular momentum remains constant. So dl by dt is 0, which means that L remains constant. What is L? L is nothing but I omega. Since here, what is I? I is a moment of inertia, and this omega will also be changing before and after the process. So before it is equal to omega I, and after it is equal to omega F. So the product of the initial angular momentum is I omega I, and the product of the final angular momentum is IF and omega F. If any of the parameters are known, the unknown parameter can easily be identified by using this again conservation of angular momentum. So since there is no torque is there in the system, the conservation of angular momentum helps us to identify or to find out the unknown parameter, either it's on final velocity or the initial angular velocity. Again, this is a good example. So a good observation is we would have been observed a cat which always lands on its feet. Do we have thought why cat always lands on its feet? Yeah, because when cat stretches its body along with the tail, its moment of inertia increases. As there is no torque which is acting on the system, the angular momentum will be constant. So when I increases, omega decreases, or when omega decreases, I increases, and which helps the cat to land always on its feet. Or we can say that a free falling cat cannot alter its total angular momentum, but by swinging its tail or by twisting its body, so it can alter its moment of inertia, which helps to alter its orientation, which means that the angular momentum remains conserved in all the cases. So this is one such good application about the angular momentum. Another interesting application about the angular momentum is the principle at which the seesaw works. We all know how the seesaw works in the parks. Children will always play happily in the seesaw. For example, you can imagine one children is sitting on the one end whose force will be equal to m1g, and the other children is sitting on the opposite end with the force which is equal to m2g. And where the seesaw balance each other at the point called A. How? So it just again based on the conservation of angular momentum, we can say that dl by dt, or which is equal to torque tau, which is equal to 0. What is torque tau? Torque tau is nothing but again I cross R. What is I? M1, M1 cross R. That is F cross R. What is F? F is nothing but M1G cross R. So the torque tau is nothing but due to the first force and due to the second force, when it is added together, will be equal to 0, which means that we can find the point at which the both the children balances each other. That is the point at which the center of mass becomes 0, or we can say that the point at which the angular momentum is conserved helps us to identify the point where the both the masses balances each other and both finds their own equilibrium position. So this is again a good such example. So to summarize the things what we have seen today is we started with the angular momentum, and we discussed about the few examples of angular momentum, and we end up with the applications of angular momentum. So for any other clarifications, just mail it to me and we'll see you in the next module. Thank you.